Now we'll study the effect of pressure and temperature on Rankine cycle. The performance of Rankine cycle can be improved by varying the pressure and temperature as discussed below. One is effect of condensate pressure. Okay, so you can see this PV and TS diagram. Here 1, 2, 3, 4. This is the original Rankine cycle. 1, 2, 3, 4, 5. Okay, but if I reduce the pressure, this is the condenser pressure PC. Okay, if I reduce the condenser pressure to 2 dash 3 dash here, okay, then the revised cycle will be 1 2 dash 3 dash 4 dash 5 dash. Okay, and similarly here 1 2 dash 3 dash 4 dash and 5. Okay, this is what will happen if I reduce Rankine cycle 1 2 3 4, decrease condenser pressure Rankine cycle 1 2 dash 3 dash 4 dash. From the TS diagram, it is clear that the decrease in the condenser pressure from PC to PC1, PC to PC1, the area of the cycle diagram increases by a certain value. This is shaded area. Area increases, okay? And this area represents the increase in work done by the turbine. In the PV diagram, it increases the work done by the turbine. Hence, thermal efficiency increases, okay? But decreasing that condenser pressure is limited by the temperature corresponding the condenser cooling water. See here, whatever we are cooling this vapor, it depends on the water which is cooling the condenser itself. Okay, so that that is why the condenser works at very low pressures, but the limitation is the condensing cooling water temperature. Okay, similarly effects of boiling pressure. Now you can see the effect of boiling pressure here. Now instead of original T1 pressure, I increase it to T1 dash. So you can boiler pressure was this one 1 2 3 4 for the original cycle. 1 dash 2 dash 3 dash 4 dash is the cycle with the increased pressure. So what happens here also, you can see the here the heat rejected. Rankine cycle is 1 2 3 4 5. Increased boiler pressure is 1 dash 2 dash 3 dash 4 dash 5 dash. Now the heat rejected in the TS diagram, you see here 2Ca3, this is the original heat rejection, but because of high pressure the heat rejection is 2 dash B dash A3. So this is reduced. So because of reduced heat rejection, the efficiency of the cycle increases. The heat rejected is reduced, and with the increased boiler pressure, that is heat rejection given by the area 2 dash 3, that is 2 dash B A3 is less than 2C A3. Hence, less heat rejection implies increase in the thermal efficiency. Thus, increased boiler pressure increases the thermal efficiency of the cycle. In real life, you find boilers working at very high pressures and condensers are working at very low pressures, even lower than the atmospheric pressure. Okay, this is a real life condition. So, increase in the boiler pressure as well as a reduction in the condenser pressure will increase the thermal efficiency of the Rankine cycle. So you need to practice this diagrams sketches very properly so that you are able to tell this. Here the only criteria was this heat rejection. Okay, so you can see 2CA3 is greater than 2 dash BA3. This is the heat rejection. This is the heat supplied. This is heat supplied and this is the heat rejection. The heat rejection is less, that is why efficiency is more. And here and here uh, the thermal efficiency increases because the work done is more. Here the work, this shaded area is the work done. This work done is more, that is why the thermal efficiency increases. But now this temperature, this temperature you see here, condenser temperature, this is a limiting factor. Whatever water is available at the temperature, you cannot go beyond that. So that is a defining temperature. To it, to what extent you can reduce the temperature of the cooling water, and hence the to what extent you can reduce the condenser pressure. Thank you.